I'll talk about today about matching markets when preferences are random. There's a lot of literature in matching markets starting from the multiplicity of stable matching that is causing us trouble to understand which kind of stable matching to, for example, to implement in a centralized matching market, or even to what kind of outcome to predict in decentralized matching markets, or even in a centralized matching market, what will happen because of the multiplicity issue. So just a reminder, I hope by now everybody knows what's a stable matching. So I'm gonna focus the talk on markets when there's the marriage market, when there's men and women. Sometimes I'll mention about more general settings when there's many to one, or if I'll have time, I'll talk also a little bit about couples. And just a reminder from yesterday, the set of stable matching is a lattice, and there's the men optimal stable matching and the woman optimal stable matching. Okay, in a setting when every agent has strict preferences over the other side. Every man has strict preferences over the women, and every woman has strict preferences over the men. So multiplicity, Knut already showed that the set of stable matching, or the core allocations in this market, is a lattice, which is huge problems for economists to understand how to predict what's going to happen in the market, or one of the fundamental questions: who is going to match? What do you expect to match to? Who are you going to match? In '99. Elliot Pearson and al. Have reported that in the National Residency Matching Program, the core is actually small. So when they took reported preferences and ran the deferred acceptance algorithm from the hospital proposing and the doctors proposing, they found out that actually there's, at least with respect to those preferences, this core is small. There's other works, empirical works, that looks at online dating and the Indian marriage market, that they estimate preferences, and then they find out through using the Gale-Shapley algorithm that actually the core is small. Okay, so they really have to go and use deferred acceptance algorithm to understand what's going on, to see that those two extreme stable matchings are actually the same. So following this work, or even before this work, there was already people tried to understand how large is the core. And there was so I'll talk about matching markets when preferences are random. Think about a set of n men and n plus k women. K can be anything. And most of the first part of this lecture, I will think about complete preferences when they are drawn uniformly at random and independently across agents. Okay, so you have every man ranks every other woman uniformly at random. Sometimes I will say different things. And also every woman has the same kind of distribution of preferences over, draws preferences from the same distribution over men. Okay? So questions that I will look at here, we'll think about is, one is, take a stable matching. What is the average rank of the men in this stable matching, and what is the average ranking of women in this stable matching? So instead of thinking about utilities, cardinal utilities, we'll just talk about the average rank. What do you expect? Where in your ranking list do you expect? Who do you expect to match to? Okay, so this is in a given stable matching. And we're going to look at we're going to average over only the people who are actually matched, because there could be more women than men and so forth. Okay? And another measure that is used in the literature, we'll look at that actually is looking at multiplicity. How many agents actually have multiple stable partners? Okay, so this tells you if you're an agent in the market, and it's not very likely that you have multiple stable partners, then you can think about this as the core is small. But if lots of agents have multiple stable partners, then things become more problematic, and you need to start thinking about behavior in this market, and and what kind of stable matching to implement and things like that. So there's lots of literature that was driven by the multiplicity about implementation and strategic behavior and issues like that. Okay? So here's some early results by mathematicians and computer scientists, Boris Pitel, Knuth, Motwani, and Pitel. And this, and they consider the market that I just mentioned, and with complete random preference list. And they say the following: with high probability, the average ranks in the men optimal stable matching is the following. For men, it's log n, and for women, it's n by log n. So think about if n is 1,000, log n is about 7, n by log n is about 140, something like that. So it's a huge difference if you are... What is it? No, this is men optimal stable matching. Okay, so think about to reach this, you can get to it for example, by the deferred acceptance algorithm using the men proposing. So it's a huge difference here. And in addition, almost everybody has multiple stable partners. So if you have such a market that, think about a market like this, you might start thinking about manipulating, for example, if there's a centralized stable mechanism that is looking to implement the men optimal stable matching, I should be worried as a woman and start maybe truncating my preferences to get closer maybe to the woman optimal stable matching and things like that. So there's lots of literature about this. I'll mention some of this. Okay, so ignore this last sentence. I don't know where I forgot to drop it. Okay? Okay, is this okay? So you see the huge difference here in the rankings. So I mentioned Roth and Pearson did find a small core with respect to the reported preferences in the National Residency Matching Program. Now, I'll talk to you about this yesterday. One thing that you see in practice is that the list of preferences of doctors is actually short. And part of this is because there's only much time to interview in the market. So, Nicole Limorlica and Muhammad Madian, they came up with a paper that, a very nice paper that formalizes a conjecture by Roth and Pearson how to explain this. And so they consider a market with n men and n women, where men have short uniform at random preference lists. It's important to say here that the preference lists are actually still exogenous here. And by short, I mean that the preference lists are of constant length. They don't grow as the market grows. Okay, so those results that I'll show, also the previous results, are results that think about n is large. I should have said this also here. N is large. With high probability, think about something that is converging to 1 as n grows large. Okay? Okay, so they look at when men have short preference lists, they only rank every one of them ranks a constant number of women. Women may have any preference list. And in this kind of market, there's only a small fraction of agents that have multiple stable partners. So essentially, the core is small. And there's a nice theorem that says that if there is no multiplicity of stable matchings in those kind of markets, one-to-one matching markets, there's no reason to manipulate. So if you're in a centralized market, you cannot influence the outcome in your favor. Okay, so it's and then Fujita, Kojima, and Parag Patak extended this result to look at many-to-one matching markets. They focused how likely is it to manipulate, and essentially showed also that the core is small in those kind of markets. Again, when the preference lists are short over it. So this result is giving some structure of things we see in the NRMP. They put preference lists to be short and so forth. So I want to go back now. I want to give a slight overview before I go to some newer results. Okay. So I mentioned the result by Pitel that there's a very large core. The difference between the men optimal stable matching and the woman optimal stable matching is huge. It's log n versus n log n. We have those those results that are try to explain the small core in the NRMP, and we have those empirical results, more empirical results that the core is actually small in practice. Okay, so on one hand, we still have those large core starting from Knuth and then all those, some markets. So what is going on? Is the core large or is it small? And what do people should expect to match? Should they expect to match to people higher in the list, lower in the list, and things like that? It's important to say also that those empirical results, in order to understand who matches to who and how big is the core, they use always the deferred acceptance algorithm. They don't take like market characteristics and say, here's the outcome, that here's who you should expect to match to. Okay, so because of the multiplicity issue, we really need to run this algorithm to see what's going on. Okay, there is some comparative statics by Crawford that says if you add one man to the market, the men are weakly worse off in the men optimal stable matching or in the woman optimal stable matching in a given outcome. Okay, yes. Yes. So here in these results, these are random preferences. In these results by Nicole and for Parag, Patak, and for Hito, there is also random short lists and random preferences on one side, but arbitrary preference list on the other side. So there is no correlation. There's no correlation. Right now, I'm. So in fact, so we'll get to that. But in fact, the more correlation there is in the market, if we agree who is what is the most favorable position, what's the second favorable position, and so forth, you expect that the core will be smaller, right? Because then it's more and more assortative. If both agree on the so side, okay? It's in some sense, think about this as it's harder and harder to have a small core the more uncorrelated the preferences are, okay? Okay, so let's go back to this result by Pitel with, again, complete preferences, uniform at random IID. This is a little bit disturbing that we still have generally a very large core. Okay? So when you run men proposing, men are much, much better off. So now a question for you. Suppose there are now n plus 1 men. Let's add some competition to the market. There's n plus 1 men and n women, and men are still proposing. So what's going to happen? Will men still have a huge advantage? Who thinks, this is actually some questions were posted in some blog posts. So men are still proposing, this is by Gil Kalai's blog post, and he wrote this question for the public, and he said, so who thinks the men will still have a huge advantage if you propose? You just add one more man to the market, so in terms of average rankings. There's just one more man. There's n plus 1, there's 1,001 men, 1,000 women, and men propose, still random, uniform at random preference list. Will men still have a huge advantage, like get a much better ranking? Who thinks that men will still have?
The men who are matched.
The men who are matched. Yes, you take average ranking over the men that are matched. Who thinks women will have a huge advantage? Who thinks something else will happen? Okay, so lots of people didn't raise their hand. Okay, what? Exactly. Okay. Okay, so here's some results from the blog. So this is what lots of people thought that men will still have a huge advantage. So these are, think about these are very heterogeneous preferences, and the market is slightly imbalanced. This is what people were thinking. Okay, so the result that I show you is that matching markets are very, very competitive. So if you add just one more woman to this market or one man to this market, the short side still remains better off, no matter who proposes. Okay, so the core shrinks. There's almost a unique core, essentially a unique core. Almost everyone is going to have a unique stable partner. And you can think about this as the short side is actually choosing, almost like ignoring preferences over the other side of the market. Okay?
Even though the others are choosing.
What?
Even though the other side is...
So even though the other side maybe is proposing, it's like the short side is proposing. It's essentially this. So there's almost a unique outcome. So the core is small, and there's very little difference between those, the men optimal stable matching. Essentially, it's the same. Okay? So, and you should think about this despite despite there's uncorrelated preferences, and that everybody ranks everyone. Yes? So,
the function that calculates the stable matching is the argument of the short, the longer side is very low. It depends on the result, something like that.
So in this, they get in terms of the average rank, they will get the same as if we ignore the women's preferences and women choose randomly one by one, in a random order, who to match to. Okay, in that sense, I will show. So let me just, so this is unbalanced matching markets. Let me just go for a second back to, I wanted to mention this, to those results that look at short preference list. So they do look at, they look at n men and n women, or when this number of positions is the same number of doctors or things like that. But essentially they're looking at highly imbalanced markets, because if everybody ranks just a small number of people, there's going to be a huge coordination problems, and lots of people on the other side are not going to be matched. So essentially, they're looking at a very competitive market. That's the way, at least I view those results. Okay. Yes.
More or less, never have them almost that you have an even and completely balanced market, right? It's enough with just one.
Exactly. So those balance markets by those results of balance markets by Pitel and Knuth Motwani is just a knife edge case. Yes.
Oh,
Yes.
you have suggested you should look at choosing the number of men and women at random also.
To choose the number of women and men?
If you're modeling,
Yes.
you might want to choose. Let's say it's not hospitals and
Yeah.
let's say a case where they're roughly equal.
Yes.
Then if you're trying to look at average results, you might want to make the numbers random variables also.
Yes. So if the number of random variables then and the market is quite large, then it's very unlikely to happen. Yes. We can formalize. Yes.
But that means there's a big swing.
There's a huge swing.
Bimodal distribution.
Exactly. So it's a real threshold of what's happening in the market. And then maybe people should start thinking about outside options if you're on the short. Yes?
I understand that these results rely on like a uniform distribution on the type profile.
Yes.
How sensitive is that to changes in that distribution?
So we'll get to that. But right now, it's quite robust. The core is small. The more likely the more correlated the preferences are, the core. We don't formalize this, but there are some results that said, but you expect it to be smaller and smaller. We do some simulations. The ranking is a little bit more fragile, and if you add a little bit of correlation, it will still stay. Of course, if everybody agrees who is the most top woman, who is the second top woman, and so forth, it's like women are choosing, no matter who is the short-sighted and long-sighted. Okay? So you might worry that those results are in just for very large markets. But here's a simulation in almost every market we simulated. Just for the number of women in the market is 40. And here we take different markets with there's different number of men in the market. So this is the market when it's balanced, when there's 40 men and 40 women. The y-axis is the average rank of how men rank their partners in the stable matching. And we look at the men optimal stable matching and the women optimal stable matching. So you see that only the balanced market there's a big difference between the men optimal and the women optimal, the average. You add one woman or one man or one less men, there's already the core swings. Okay, and So this is in terms of average ranking. Here's what I said about if you ignore women's preferences and let men choose in a random order, so you cannot choose someone who's already chosen, and you look at what's the average rank, you see it's exactly the average rank. When there's more women than men, you get the same average rank. So you get the average rank in the matching market as if you ignore the long sides preferences. So in that sense, we call it the short side chooses. Here's what happens to the core. How many people have multiple stable partners? When the market is balanced, you see this is the percentage, about 60-something% of agents have multiple stable partners. Okay, so the way you check it is just you run the men optimal deferred acceptance, the men proposing deferred acceptance, the women proposing deferred acceptance, and see how many people get different matches. And it quickly shrinks down. So here's a formal result. We consider again this market. Now we add competition, so there's n plus k women. The n over 2 is not very important. Just to make this precise here, the more imbalance in the market there is, the better the short side is. So the average ranking of men in any stable matching, men optimal, women optimal, is about log n over k. I will put some specific cases later when there's just one or many more women. And the average ranking of women is as bad as n, pretty much n by log n. Okay, so that's the result. And you see here that this result, little o of 1, is something that converges to 0 as the market grows large. So the average rank of men in the women optimal stable matching is pretty much, it's not far from the average rank in the men optimal stable matching. So they're essentially the same. And the core is small in this sense that most people have the same stable partner in all stable matches. Okay, so again, this is the summary of the results. So men do almost as well as they ignore the other side's preferences and just choose in random order. Okay? And women we should also say that women, you should look at the average rank of women as if they are just getting a small random set to choose from. So they're almost getting randomly chosen. Okay? So this is the result if you add just one woman. So it's about log n. It's really something that converges to 1. This I just put here 1.01 and n by log n. Okay, again, and just to emphasize, here's some numbers. If n is 1,000, this is the log n and n by log n. If n is 100,000, log n is about 11. N by log n is about 10,000. So we need to think about those. Both of them, if you divide them by n and let them grow to infinity, converge to 0. But we need to think about realistic sized markets, and this is a huge difference. Okay, here's what happens if you add a linear fraction of agents on the other side. Then the average rank of men is a constant, some constant, and the average rank of women is n over a constant, like you get really randomly chosen. And this result is actually not very difficult to prove. You don't, if there's lots of extra women in the market, then men will start proposing maybe to the first, the second. Very quickly, they will find a woman that is just not much to anyone, so they will get a very, very high rank. Okay, so you expect that men will do very well in the market when there's lots of extra women. Okay. Yeah.
What was the correct answer for this poll?
Correct answer for what?
For the poll.
Oh, what is the correct answer? The correct answer is that men are doing, so that's what I hope that was, men are doing much better off, even if they're on the long, women are doing much better off if they're on the short side of the market. The short side of the market does much better off, are much better off. It doesn't matter who proposes. Okay? That's basically that's what's important. Being on the short side. So it's like classic economics. Being on the short side is what's important. Yes. If there's what? Yes.
independently, and there is agreement among the men only on the attractive women, only on a small
So on
part.
one side there's agreement, on the other side,
Only on the small part.
The top 10.
Yeah,
Top 10 are,
yeah, there is agreement that
so those are specific markets, and then you should maybe solve that top tier, what's happening there, and then see what happens in the remaining of the market. So,
then it unbalances the equal side.
so that's a very important point. So who is the short side and who is the long side is not always clear just from the numbers. You need to think, what are the tiers in the market? Where is my position in the market? What is the effective market that I am part of? Just from numbers, seeing the numbers of the job market or the number of people is not. So we need to put more more structure, understanding what market are you actually playing. Yes.
So basically, if the large size of the market, instead of being given as a function of n, it's a fixed number. Could my intuition says that the difference between the rank of men and women should converge to to the same thing or not?
No.
So saying you fix a number, for example, number of more you have 100 more women.
Okay.
So
the,
as n goes tends to infinity, what will happen in that case?
oh, so that's tricky because you converge to 1. The ratio converges to 1. As long as there's always at least one more women in the market, then men are doing much, much better. Yeah. Yes.
The short side are getting better off. It's only with aggregate level. So it is not necessary that every agent in that short side is getting better off.
That on average, the short side. So this is so you're talking as per every agent by the distribution.
Someone is getting much better off, but someone is also getting worse off. So on average, but they are.
So the average will stay log n, but the worst rank of an agent on the short side will be about log square n. But all agents are not all agents. We didn't analyze the distribution, but we can say something about how the worst agent is doing, and the average. But those are interesting questions to look at this distribution. Actually, yes. You have to speak louder.
So it's similar to the transformer distribution.
Yes.
Where you add one man on one side, the payoff.
Oh yes, yes. I will talk about this. That's exactly right. So the left shoe, right shoe, for example. Yes, that's exact. I'll mention that. Okay. So again, strategic implications mean that if the core is small, there's no reason, stable centralized mechanism to actually misreport your preference. You cannot really, if everybody has a unique stable partner, there's no reason to almost everyone. There's no reason to believe that it's going to be you that have multiple stable partners. You might actually end up not being matched if you misreport your preferences. So I won't formalize this, but yeah. Manipulation is very limited. So again, this is exactly what you're saying. So in matching markets with transfer and Shapley-Shubik model, so you can look at, here's a simple model that there's n homogeneous buyers, so everybody is selling exactly the same good. And homogeneous buyers, everyone has unit demand from n homogeneous sellers that are selling all the same good. In this market, every price supports a core allocation. Okay, but if you add one more seller to the market, immediately the only price that supports that is competitive is 0.
With money.
This is with money, and this is also when everything is everybody has the same value for each good, so it's homogeneous market. Okay, so there's no heterogeneity here. So you add one seller, there's a unique competitive price. Okay, so essentially this is what we see here, but things are more complicated. We have heterogeneous preferences, and we don't have money. Okay, so some intuition for what's going on is that if you add there's one more woman in this matching market, then men are supposed to be weekly better off. But that extra woman is, not everybody maybe wants her, but some men will want her. So then those men will be better off because they have a nice outside option now. And some of the women that are matched to those men are going to be weekly worse off. So those women that are matched to those men are going to create an outside option for other men. Someone will want them, and they will create and these outside options are going to ripple throughout to the entire market. Okay, so someone is happy that some man is happy that some other man likes that extra woman. So that is roughly what's going on. Let me give another intuition through the rural hospital theorem that you heard about yesterday. So the rural hospital theorem tells you that in all stable matches, the same exact woman will not be matched. That's the rural hospital theorem. Okay? So think about now there's n+1 women and men. It's going to be hard to make at the same time the average rank of men much worse than log n or bad, and at the same time that no man will want this, and find us at the same time a woman that no man will want to deviate and go with her. Okay, so it's hard to make things bad for men so much such that no man will want this extra woman that is in the market now. So that's for the intuition from the rural hospital theory. But this is really economic intuition that there's a chain of outside options that ripples through the entire market. Okay. So let me give a proof overview for this. How we do this. So first, what we want to do is start with an algorithm that men propose and reach the men optimal stable matching. This is the structure of, we're proposing an algorithm, and through that algorithm, we're going to count proposals. So we're going to start with the men proposing deferred acceptance algorithm to reach the men optimal stable matching. And from there, we're going to continue in a similar fashion of deferred acceptance to find the woman optimal stable matching. And throughout those algorithms, we're going to count, we're both going to count how many proposals are made, but also who is matched to who in this market to figure out who has multiple stable partners. So I hope that this will be more clear now. So this is the men proposing deferred acceptance algorithm. Again, everybody proposes to his favorite woman. Women that get multiple proposals reject the men that they keep temporarily only the men that they like the most, and men keep on proposing until we reach the men optimal stable match. So now, we reach the men optimal stable matching, and now I want to propose this algorithm that extends algorithms by McVitie-Wilson, if you heard, to reach the woman optimal stable matching. One thing to note is that until this phase, using the result by Pitel, there haven't been too many proposals. There's roughly men did on average log n proposals. We just added one more woman to the market. The situation of men is, by Crawford, is only weekly better off in the men optimal stable matching. Okay, so the men essentially didn't do too many proposals up to this point. Okay, so how do we get from here to the woman optimal stable matching? So the idea is that I want to check for some woman that is matched to her worse stable partner now. I want to check if she has a better stable partner. So she will divorce this man. She will trigger a rejection chain. So this man that she divorces is going to start applying down according to his preferences, just like as in the deferred acceptance algorithm. And so he starts applying until he gets a position, and maybe this finds a woman that likes him, and she rejects the man that she's matched to, and so forth. This kind of rejection chain that this woman that I want to check if she has a better stable partner, this chain that she triggers will terminate in two ways. One is that it will terminate in so let's call this woman W hat. if the chain goes back to her and she accepts she finds a better match, she finds a better stable partner. So then that's an improvement phrase. We call this for W hat. So she finds a better stable partner. Another way that this chain will end is with the woman that is unmatched, or one of the women that are unmatched. In that case, we know that by the rural hospital theorem, that the W hat doesn't have a better stable partner. Okay? So we're going to do this woman by woman and always keep up the, record the matching that we got to until we reach the woman optimal stable matching. I will illustrate this next, so I hope if it wasn't clear, then, so we do it for every woman in the market until we reach the woman optimal stable matching. So maybe best is to illustrate this algorithm. So suppose now we found the men optimal stable matching. And woman 1 in this matching is matched to M1. So this M1 is her worst stable partner, right? Because it's the men optimal stable matching is the worst for the women. So to see if, I want to see now if W1 has a better stable partner. So she's going to reject M1. M1 is going to continue proposing as if it's in deferred acceptance down his list. So he tries to propose to some other woman. Maybe she doesn't like him over her current match. And then he proposes to someone else. And then he finds a woman that likes him over her worst stable partner, or her current stable partner, M2. So W2 likes M1 more than M2. So M2 has to go and keep on looking. So he proposes to the next woman on down his list. And eventually he finds a woman that accepts him over her current match. This is M3. M3 continues to apply. This is the chain. And maybe one possibility that this chain will end is with W1, who likes M3 better than M1. What does that mean for W1? What did we find for W1? No, let's not think about manipulations here. A better stable partner, right? Of course, it's related to manipulation, but a better stable partner. So M3 is a better stable partner than M1. Okay? What about W2 and W3? What about them? Also better stable partners, right? It's a stable improvement cycle. Okay? So all of those three women now we found from them a better stable partner. We keep this match. We now update the match that we found so far, and we keep on going. Okay, so W1 is now matched to M3, W2 to M1, W3 to M2. I want to see now maybe W1 has even a better stable partner, so I will just continue with this. So she's matched to M3. She rejects M3. M3 goes and proposes to his next preferred woman, and the same process happens. And now maybe the chain goes to this. Let's say there was just one n plus 1 woman, and this W bar is the extra woman. Maybe this chain went to W bar. What does this? What can we deduce from this? So what does W1? What can we say about her? What is it? So there's no better stable partner than M3. What about W4 and W5? Could they have a better stable partner? Could W4 have a better stable? So W1, if she rejects M3 and the chain goes here, by the rural hospital theorem, we know that she doesn't have a better stable partner, because if she rejects someone, the chain goes to this unmatched woman who cannot be matched under any stable match. Okay, so what does this mean about, what about W4? What is it? What is M4 her best stable partner or not? Okay, so who thinks the M4 is her best stable partner? So why?
We do the same exercise.
Okay, so if M4 is W4 now rejects M4, we know exactly where this chain is going. M4 is going to apply to this woman, and it's not going to be accepted. Then she's going to apply to this woman, and so forth, and it's going to get here. So we know now that not only W1 is matched to her best stable partner, but also W4 and W5. Yes?
Is that the same as the stable improvement cycle in the one that they do in their paper? Is that the same as Erwin and Ergil pairs on stable improvement cycle?
So the same combinatorial arguments, yes, but yeah. But they looked at matching markets when there's ties and things like that too in order. But
apply the same idea to reach
it's a combinatorial result here. It's not a stochastic result, but yeah, you get to a better stable partner if it goes back to you. Yes. Okay, so all these women, we already know that they're matched to their best stable partner. Okay, so keep this in mind. So now so we know now not that those three, but also this one, we know that this woman also doesn't have any stable partner because we know by the rural hospital theorem. All of these women, we're done in the algorithm that goes to the women optimal stable matching, we're done. Okay, so now we go to the next woman. W8, who is matched now to M8. She rejects, we want to see if she has a better stable partner. She rejects M8. M8 goes and apply. What happens if she applies to W4 and W4 likes M8 over M4? What happens then? What is it? It's the same thing, right? So if W4 is going to accept M8, she prefers M8 over M4, we know exactly where the chain is going to be. We know already that W4 is matched to a stable partner. So if she accepts M8, we know exactly where this chain is going to. So any chain now, any woman that is, by rejecting her current husband in this chain, is going to reach this set of women that we already found for them the best stable partner, we know that these kind of women also found the best stable partners. And the idea of the proof is really to show that this set of women that we found from them the best stable partner is going to grow very, very quickly. Already we can find for the first women, we can find a woman that this chain will include lots of women. By the way, the chain that ends in this unmatched woman, we'll call it a terminal chain. Okay. So we add W8 to this group and so forth. Okay, so roughly, again, you don't need to read all of this. We keep track of a set of S, which is the set of women that are already matched to the best stable partners. And we look at all the women that are not in this set. So this set is initialized to all the women that are unmatched at the beginning. And each time a woman in those phases, each time we check if a woman has a better stable partner, if this chain goes to a woman in S and she accepts it, we stop. We add this woman now that we checked if she has a better stable partner. We add her to S. Not only her, all the women in this chain that accepted men in this chain that just reached this set S. Okay, so this is the algorithm. I'll give. So again, the idea of the men proposing deferred acceptance part. So we start with the men proposing deferred acceptance, and then we move to we find the men optimal stable matching, and then we continue in a similar fashion to the women optimal stable matching. The number of proposals until the men optimal stable matching is similar to Pitel, in which you use something called the coupons collectors problem. So the coupon collector problem, if you're familiar, think about there's n plus k coupons, and you're trying to draw without replacement, with replacement, n distinct coupons. And each time you find a distinct coupon, it's going to take longer and longer to find a new distinct coupon, right? So every time it's a geometric distribution that has a different parameter, and the time that it will take you to find n distinct coupons in this kind of problem is n log n, pretty much. So you can bound those numbers until how much, and you average over n, so it's log n on average for each, it's log n average for the men. So there's a very close, you bound it from above and below, and you see that this is the number of proposals until that point has not been too much. And now we want to count proposals and also see who is matched to who until we reach the woman optimal stable matching. So, and the idea is that this set S grows very, very quickly. Let me give you a little bit of intuition why it grows very, very quickly. Okay? So think about first of a market that there is many, many extra women, a linear fraction. So already S is very large. Okay? So that almost every chain is going to immediately go to S. Okay? So that's an easy part. But what happens if there's just one extra woman? Okay. So let's look at the first terminal phase. Okay? So we started with woman 1, and she rejected M1. And there's a chain that chain could have gone either back to W1, who might have found the best stable partner, or it was a terminal phase that reaches W bar. Now remember, there's n plus 1 women and n men. So it's going to take, men didn't do so far many proposals. So roughly they apply to each woman with probability 1 over n. Okay? Each woman that they didn't apply to, approximately 1 over n. So this chain is going to be, the length of it is going to be pretty much a geometric, follow a geometric distribution with 1 over n. So it's going to involve about a linear number of women. Okay? Okay, so until it terminates. So every proposal is not very likely to go to W bar. It's only with 1 over n percentage. Okay, so that chain is going to be very, very long. Okay? One thing that I am not telling you is that this very, very long, the first very, very long chain is going to maybe have some cycles in it. Okay, and we need to count those cycles. So if you take it into account those cycles, there is this, if you're familiar with the birthday paradox, then the real first terminal chain will include only about square root n women that are going to join this set of the set S. So, but square root n is already quite large, and we need to continue the analysis, and very, very quickly everybody is matched to their best stable partner. So that is what's going on. So again, just take the first women that we start with about probability 1 over n, the chain is going to go back to her, and probability 1 over n is going to go to W bar. In fact, we can find a woman that it's more likely to be, the first phase is going to be a terminal phase versus an improvement phase. And that first chain that is going to come to W bar is going to be very, very long. So already in the first phase, we're going to add lots of women to this market, to this set S. Is there questions on this? Yes.
By cycle, do you mean that we go back to W1 and then do the rejection?
No, so it could be that the chain goes W1, W2, W5, and maybe this is again W2. So if it's W2, W5, W2, this is an improvement cycle for those 3 women. Okay, so if I count just how many times each woman appeared once, it will involve pretty much the order of square root n. Okay? There could be larger internal cycles and things like that, but yeah. Okay. Correlation. What about more correlation in the market? So first, perfect correlation, of course, leads to a unique core. Okay, if everybody agrees who's the most favorable woman, second favorable woman, everybody agrees who's the best man, second man, then of course we know what's going to happen. Who's going to match to who? Okay, but we need to, if there's markets with tiers, so there's a bunch of jobs that everybody likes more than some other jobs, then you need to look at those tiers and understand understand better what is the short side and long side. You need to know which market you are at. So for example, if you have 15 men, 20 women, and let's say there's 20 women who could be distinguished, the top 10 favorable women and 10 less favorable women. And inside these women, there's heterogeneous preferences, so uniform at random, for example. Okay? So then to solve this market, you can still see that the core is going to be unique here, because first you look at the market with these 15 men and these 10 women, and then look at the remaining men and solve the market with the remaining men and those 10 mid women. Okay? So, and then you need to fit, so in those kind of markets, we also know that there's a unique outcome. Yes?
Men are the short side units, so they have disadvantage. The advantage of being on the short side, but the advantage of being on the short side.
Yes?
But
But
they have disadvantage from having positive correlation, right? We're talking now about relative magnitude.
so here, let's say there's random preferences for men over those 10 women, and then there's random preferences
All
for,
the men agree about the top 10.
yes.
So there is a correlation.
Yes, there is some correlation in this market. So here,
Correlation can be large enough to outbalance, to be more
they don't agree here who is the best woman and so forth. They just agree that those top 10 women are better than those 10 women. And in these 10 women, they have still random preferences. So that means that men are not actually doing so great, because this first market only for the top women are with these 15 men, and men are not going to do so great. So you can, in this kind of markets, you can do some calculations, use the result, apply the results we have, and see what happens. So at least in the top market, you know what's going to happen. You know that you can give a lower bound on the average rank. You can say the average rank is going to be at least this amount, right? But another important thing here is that you know that the core is going to be, there's going to be a unique stable matching, essentially a unique stable matching. Okay. But the message here is that we can deal with tiered markets. Maybe there's idiosyncratic preferences in this market that we're looking at, that we are effectively part of. There's different types of correlations that, of course, need more attention. But we did some simulations, and here's some sort of correlation that we did. We took logit preferences, and we say the utility for man M for matching with a W with, let's say we index the women, and he matches the women index W, is beta W plus epsilon. Epsilon follows an extreme value 1 distribution. So that's, if beta is huge, everybody agrees on who's the best woman, who's the second, and so forth. Beta is 0, we're back to the uniform at random case. Okay, so the complete heterogeneous preference. So this is what happens in the market. This is the men average ranks of wives. This is the brown is the percentage of multiple stable partners. So it's not monotone here, but you see the percentage here. This is the percentages that doesn't go very high. It goes up to 5%. And the blue and the red are the average ranks in the men optimal stable matching and the women optimal stable matching, the men's average rank. And the green is what happens to the average rank if you ignore women's preferences. Okay, so it's not monotone, which is maybe kind of surprising. I don't have a great explanation for this, but this is what happens. But again, the percentage of people that might have multiple outcomes is not large.
To have multiple stable matchings, you need some of those cycles that you showed us.
Yes.
And correlation works for, the more correlated we are, the more likely we are talking to the same people, but the less likely we disagree about
Yeah, so here there's uniform random preferences on one side. On one side, I'm putting some amount of correlation. It's not monotone. Again, these numbers are not high, but something is going on here in the sense that it's a little bit of correlation as if it balances somehow a little bit the market. I don't know how, but it doesn't grow to the numbers of 60% or 70%. It's still small.
To get cycles, you need both that men are talking to the same women,
Yes.
but that they disagree over which one is better. So it looks like there's a sweet spot in the correlation where we're talking to the same. When there's too much correlation, we don't disagree.
Yeah.
We talk to the same women, but we don't disagree about them. And when there's too little correlation, we're not talking to the same people. It looks like we're
Yeah.
finding the place where the same group of men is.
Yeah, so I think that's kind of an intuition. I'm still not sure where exactly it is, but yeah, this is really a little bit of correlation. Now notice if there's zero correlation, men are doing really well. If there's a lot of correlation, it's really a woman choosing market. So the women are choosing even if they're on the long side. So men average rank is becoming bad. Okay, if everybody agrees who's the best woman, then women are choosing in this market. Okay? Yes? I don't show the average rank of women here. So it will be pretty much the opposite. It will go like this. So this is men. This is a balanced market. Oh, yeah. So I don't. If you add just one more woman, I don't think we'll see a lot of differences here. So but adding correlation, the balance a bit goes away. So if the most important thing is to understand what is your market that you're playing at. If you're in the and correlation, so we're still short of understanding a lot about correlation. But for example, here, it's very important to be one of those top women. If that's more important than to be on the men's side, right? And this kind of correlation is a little bit more complicated, and I think we need to still understand. Of course, I prefer that if there's less correlation, I prefer to be a man here. If there's more correlation, I prefer to be a top woman, to choose one, to be one of the forced to choose. Okay? Here, this is the same. If you zoom into the first, if you zoom into this area, so you see that the average rank still stays small for a while. So the average rank is more fragile than the unique core. The small core, the more correlation you put in the market, you expect it to be smaller, except this non-monotonicity we need to understand. I still think it's, we should treat it as a small core. But it's an interesting place. It's been a spot to study, that's for sure. This kind of spot. I see Al smiling there, and yeah. Yeah.
Do you have an intuition where that average rank is coming from? Whether it's from a high chance of getting your first choice, but then a really smaller chance of getting something very bad, or whether it's like very balanced?
In the unbalanced,
like the rank distribution.
Yes.
So now you're looking at the average rank. So what
about the distribution you're asking? So in the original setting, we analyzed I don't know much about the distribution. I know that the worst men, for example, will get his log square n rank, but with high probability. Log square is still much better than n by log n, right? Even the worst man is still doing very, very well.
So there's not high variance.
Kind of. I think we still need to dive into this, but yeah. Here's some simulations for different size of markets. This is the balanced market. This is if you add one more woman. This if there's one less woman in the market. And this is the average ranking of men in the men optimal and the woman optimal. So you see, this is the spot that it's very different from each other. It's very important to be, if it's a men proposing or women proposing, if you run or men optimal or women optimal, and here it really doesn't matter. So another way to view those results is kind of a Bülow-Klemperer result. If you bring just one more woman to the market, it really doesn't matter who is proposing. That's my kind of interpretation, but maybe there's even a formal result here, I don't know. What is it? This is for uncorrelated, yes. Yeah. Yes. So if you run the random to serial dictatorship, it's still men choosing in this market. So the more correlation there is, it's like more women are choosing, and here you're still letting men choose, ignoring the women's preferences. Why is what? This one? Why is this one better than both of those? So here you still let men choose. It doesn't grow much. You see, that's why we showed the zoom that the difference here is still not big. But yeah. Okay. These are percentages of stable matches. Again, this is for larger markets. You see that it goes down. How many people have multiple stable partners? It shrinks very quickly. Here's even 1 million agents in the market. So you will believe simulations. I'll put those slides later on. But you see the average rank for 1 million people in the market. The average rank of men is 13.4 and 14.4 in the men optimal and the woman optimal. I guess being in the Silicon Valley is not great. But no, there's not. Okay. So here's the women optimal. No, so the women optimal, this is men's average rank. So in the women optimal, it's a little bit worse for men than in the men optimal. This is the worst optimal matching for men.
Oh, the ranks.
The parentheses are standard.
Doesn't that suggest something wrong with this model?
That what?
Doesn't that suggest there's something wrong? And with 1 million people, a difference of one should somehow, with 1 million people, 1 million of one.
With uniform preferences, with very heterogeneous preferences, the difference of so. So people complained at the time. I think people complained at the time in the left shoe, right shoe, that it's very discontinuous. I think it's now the same.
You're right. The bigger.
I think people should complain. People should complain about the balance case. Why are we seeing so many possible outcomes? And I don't know. Well, okay. Okay. So the summary of those results: the short side chooses in all stable matchings, and the core is small. And here's a general question that I think, unless there's very kind of uncoordinated preferences, I think the answer to this is yes. The core is generally small. That's what my belief is now. Okay. So no really market assumptions here or anything, and we get those. So here's some maybe questions or recent developments and some future questions maybe for research that I thought a little bit about. So one question is, why do we observe short preference lists? There's a partial reason in these results, but I think it can be more general stated. So if firms are on the short side in their market, they don't really need to interview so many people. If they have some a priori kind of ranking, they need to look at only log n or log square on at most people to interview. Of course, there's also costs for interviewing people and things like that, but I think those kind of results give you a little bit about who to expect to match to, and then maybe also directions who to interview as a function of the position in your market. There's some recent results about people looked at cardinal utilities and studied the trade-off between efficiency and stability. Lee and Yariv and Chen and Trichet about stable outcomes are not always giving efficient outcomes, and they have really nice new papers. There's a recent result by Saf Rom, where is the Saf? Here's the Saf. And Vinatan Hasidim about the Shapley-Shubik model. They look at the Shapley-Shubik with random utilities. When a utility, if two agents match to each other, they can split the utility between them. There's a random utility for being matched, and they can split the utility. And they have this one law of one price result that really the difference between the firm optimal to the worker optimal, for example, has to be very small. And then they conclude that if the market is imbalanced, the short side actually takes almost the entire surplus. But ask Asaf about this. It's a beautiful result. Okay.
I have a question.
Yes.
Especially this unbalancedness.
Yes.
When one side of the market is excess demand, right? Raise the question about the trade-off between stability and unbalancedness of the market. So I wonder if there are results that says, well, let's sacrifice stability. Let's see how, if we make the market more balanced in terms of what men and women are getting, maybe we can create matching that are almost stable. Let's say that there's hundreds of thousands of men and women.
Yes.
There's going to be only one blocking peer. I wouldn't worry too much about it if it can contribute a lot to making things balanced, especially where.
So why do you want to make things? Why do you want to make things balanced?
Sorry.
Why do you want to make things balanced?
For instance, when we have schools and like what Al described yesterday, when
Yes.
we have hospitals.
Over there, there's.
And suppose we have much less slots
Yes.
than applicants. There is a reason to make things more balanced. For instance, make sure that they are, that the students are treated better by the market.
Yes, if there's too many students, they're doing very bad, and you
Yes.
maybe want
Maybe
less
you
students
can
to
improve
admit less
maybe
students.
you can make them better off by allowing a
You-
shred of instability.
So that's a good question. There's lots of issues in not too many grad students in lots of fields that, maybe admit less students and things like that. Yes, that's an interesting direction, I think. If it's very highly unbalanced, they're doing even worse. But once it's even a little bit imbalanced, they're not doing great. But no, I agree that we should definitely, in some fields, have less. In some fields more, in some fields less. I don't know how to answer this, but the balance case is at least has problems like implementation and strategic issues, which really all this goes away if you believe the small core results. Yes, which is all the nice properties to have. Yes.
In a way, the same is true if you do correlation between sport teams and athletes in some North American leagues, such as basketball or hockey or in American football.
Yes.
And they have special draft procedures
Yes.
that I have very different from what we see here. But I intended to balance out teams in long term, so you don't have long-term leaders and long-term losers.
Yeah. So some of those. Okay. This maybe. Any other? Okay. So I have 20 minutes. Let me go over some results about markets with couples. Another type of results that Al mentioned yesterday a little bit, so I won't go over the whole story here. There's this market for residents, and there's lots of the increasing number of women over the years, and therefore there's increasing number of couples that participate, and you need to answer to have joint preferences for those couples, and that's what the reform that Elliot is going to tell you about, and I'll tell you about, that they did in the National Residency Matching Program. One reform, by the way, was to change the order of hospitals proposing to doctor proposing. They found also that there's small, the core is actually small, and it doesn't really matter much who is going to propose. Okay, so there was a lot of more people graduating as couples, and you need to let them express their preferences in this market. So here's a preference list for a couple. They may prefer, Alice might prefer, this is the first preference of the couple, NYCA, NYCX. Maybe the second preference is NYCA, NYCY, and so forth. So they list a bunch of pairs of positions. So some positions can repeat themselves, of course. Okay. Here's some numbers. There's about 16,000 people in the match. And there were about, here at 2010, about 800 couples. Okay?
Both the match in the same, right?
What?
Both the match in the same, or match in any aspect.
Sorry?
Both the match meaning
Post?
both.
Both.
Meaning they matched in.
Oh, if both of the couples were actually matched.
Not the same.
This is in the outcomes. Yes.
Just match.
Yes. So there's an impossibility result of stability when you have couples. So here's just a simple example. So I'll show you an example of instability. Did you show? So maybe I'll just go over this quickly because I'll use it a bit later. So here's those two hospitals, and this is their preferences. He prefers Alice over Charlie. This hospital prefers Charlie over Bob. Alice and Bob just prefer residency programs 1 and 2 together, otherwise not to be matched, and this is Charlie. So if Alice and Bob apply, they're matched, but now Charlie can block with resident program 2. So he goes and they are rejected because they are not happy they either match together or not. And then Charlie's happy to go to residency program 1, but now Alice and Bob can block again. So you have those cycles that are keeping on going. Okay? And then, so Al and Elliot, they found that there was a stable match, at least with reported preferences, in the last 12 years. So here, let me just give you a model and some results. So here's a model with a random large market model that has n doctors on one side, and there's extra number of positions, a linear extra number of positions on the other side. Okay, this is just one model that actually very closely related to what Al, Fojito, Kojima, and Parag Patak came up with to explain the stability in those large markets with couples. So it's also a many-to-one matching model. By the way, in all those unbalanced markets, the results hold also if you have a small capacity in each. If instead of women work as firm, and there's a small capacity in each firm. So here there's a small capacity, and doctors have uniform at random preferences. Hospitals have maybe any preferences over doctors. Okay, arbitrary responsive preferences. So the hospitals can choose any sets of doctors, but they follow responsive preferences. So they have some underlying list that they really follow through. Okay, and here's a result that Al, Fojito, and Parag showed that in this random market, when you have some number of couples, that is the number of couples grows as n square root of n, with high probability the stable matching exists. In fact, they had a slightly different model. They had this model that there's n, instead of a highly imbalanced market that I had here, I had an extra number of positions. They had a market when There's a short preference list for the doctors, but a balanced market. So again, those short lists actually create essentially a high imbalanced market. So I think there's no formal connection here. I think it will be interesting to make this formal, but that's essentially what's happening here. So here we have complete preference list. I put here complete preference list, but an extra number of positions. Okay, again, the short list creates a coordination problems, which is going to make lots of competition among the hospital sites. Okay, so when the market grows large and the number of couples is about up to square root 10, with high probability a stable matching will be found. And after the result, we extended this theorem to be able to accommodate up to n to the 1 minus epsilon couples in the market. So any sublinear growth you will still have a stable matching. So let me show you how you get this kind of result. I'll try to give some intuition just for how we construct this result. Okay, so we construct again an algorithm that will find a stable matching. So how does it work? So what we do is we start with running the deferred acceptance algorithm only with the single doctors in the market. So we find a single optimal stable matching, okay, for doctors. And then we let couples start applying one by one. So a couples apply, maybe causes some rejection chain. And then after this rejection chain settles, we let the second couple apply. It causes some rejection chain and so forth until everything settles down. But what we're looking really is that we're looking for some order of the couples such that when a couple applies, he will never cause in the rejection chain to move any other couple in the market. A couple, where? A couple proposes to a pairs of hospitals. Okay, a pairs of positions. So it could be 2 chains, yes, from that. But what we're looking here is after we find the singles optimal matching, we're looking for an order that couples will apply such that no couple will ever cause some other couple to be rejected. That previously applied and got assigned so if this is true, if a couple applies and he causes some rejection chain and by causes those rejection chain doesn't cause any other couple to move around, then you will find a stable matching. Okay? So that's what we do. And here, what can go wrong if you first start with Charlie, he finds the singles, he finds a best position. Maybe now there's only one couple here. So the couple applies, and Charlie is rejected. So they start a rejection chain, but Charlie goes back, but the couple is rejected. So that's not good. We want that when couples apply, they are never rejected or never cause other couple to be rejected. And this is something that actually happens probably. I'm sure Elliot will tell you about those kind of things. And Elliot actually found some solution here. You can actually let one of them continue applying down their list, and in the data that I looked at, it works, but those are real issues that you have to deal with, and so this happens. But at least for this model, those kind of things will not happen. What is this?
Because you have many more hospitals.
Than couples, yes. There's not too many couples in the market. So we're looking for some order of the couples that when they apply, they don't reject themselves and cause to reject, when they trigger a chain, they don't cause to reject themselves or any other couple. So it could be that one couple applies and then another couple comes and, so let's look at this. So we look at this couples graph or influence graph, and we put a link from an arrow from couple AB to another couple DE if couple AB is likely, by causing some rejection chain, to reject DE. Okay, so we do some stochastic, so we have this, we use this structure and analyze what is this graph going to look like? So again, so what happens that in this market, Alice and Bob caused a rejection chain through Charlie that will reject it will reject the same couple. So the couples graph is consisting here of just one couple, and it has a link to itself because Alice and Bob can have a rejection chain that will cause it to evict itself. Okay? More generally, here's two couples and two singles. If Alice and Bob apply and cause a rejection chain through C and D, and because of that reject another couple, and maybe when those couple apply, they cause through some other single to reject this other couple, then the couples graph will look like this. Okay? So this is the structure we put on, and in the paper we analyze what is this, how dense is this couple graph. So if this is the influences or the likely rejection chains, then this is what the couples graphs look like. So only AB is likely to reject EF, and EF is not likely to reject AB. Okay? What? This is good. So here you can just let AB propose first, and then EF propose second, and EF will never reject AB. So yes, basically, if this couple applied, who are the possible doctors it's going to influence? Yeah, I don't want to get, I don't have much time. Let's talk about this afterwards. But the answer is yes. So what this algorithm is looking for is looking for an order of the couples such that there will not be any cycles in this couple graph. And any graph that doesn't have a cycle, you can order the couples such that when they apply in this order, no couple will reject any other couple, and we will end up with a stable matching. Okay, so let me just, so if this is the graph, we have two possible orders. It actually doesn't matter which order you have, you will end up with the same stable outcome. And so so if you start with the singles, then you start with some couple applies. If some other couple rejected them, you start again, you reverse the order between them. You know that this couple has to apply first, and so forth. So every time a couple is rejected, you reverse the order of the couple that was rejected and the couple that started to apply now, until you find a stable matching. So if the couples graph is going to contain a cycle, then you are screwed. If otherwise, so then there's no stable. It's actually not completely true, but what we analyze here, they might be actually still a stable match. But to analyze, what we show is that if no couple is evicted, we find with high probability, there's no cycle in this. But in fact, there still could be stable matches. And actually, Al and Elliot have in their algorithm actually some situations that you actually need to do something like if there's a cycle kind of like the stable matching that I showed, you sometimes need to try and break it in some tie there who will continue apply down this list, and then things can work somehow. So there's a little bit of things that we still don't completely understand, but I think this algorithm is essentially equivalent, except those little engineering places, to Al's and Elliot's. So just last thing here, what we show in the paper about this this large market approach is that the probability that a couple will influence some other couple is about roughly 1 over n. And here you can see that if you have less than, for example, square root n couples will not influence each other because there's 2 to the square root n, choose from square root n, 2 from square root n links, and there is not going to be any link. But as long as the number of couples is bounded by n to the 1 minus epsilon, you can see that this, well, there's quite some analysis to do, but this graph will not have, at least a direct argument is that you won't see two-way cycles. You need to work more to see that there's no cycles at all. So yeah, so I won't go into the details here, but another discouraging result is that if the number of couples grows linearly, you still have a constant probability that doesn't depend on the size of the market not to have a stable matching. Okay, so it's kind of also a threshold result until you have, as long as the number of couples grows sublinearly, you're good. Otherwise, okay. So here's some simulation, not simulation, we checked with psychology from APIC data, Market for Psychology Interns. We look at several years of data here, how those couples graph look like actually. And here's the graph. Here's some graphs that had links. All the other graphs didn't have links at all. No couples really influenced any other couple. This is actually a real problem. This is a cycle, and those are the situations that are the most problematic. But this is not very likely. In our model, it's not likely to happen. It does sometimes happen. So we do need a little bit more structure on couples' preferences to understand more. In this paper, we do give some kind of a city preferences approach. Couples first prefer to cities, but it's still, I think we need still more than that. Here's some simulations for if the market, this is the percentage of couples in the market. So if there's 4% couples in the market, that means that they consist of 8% of doctors in the market. And this is the success probability to find a stable matching as the market grows large. So you fix the percentage, and you see, there's still some failures. But this is using the model that I described. It's a simulation result, not using the data, using the model. OK. So just, again, to summarize here, maybe more structure on couples. To understand better what's those things. What to do when there's no stable matching. So again, Al and Elliot came up with some ideas. Maybe we can formalize those and see why those things work. And actually, a very interesting question, I think, is the third one, actually. What should we suggest or recommend employers to do when they facing couples, like if you're a rural place or not a rural place and things like that. You have lots of other competitors in the city, and I think we still so we do see how we can collect data of how those employers are what they are doing, but we don't have much models for this. Yeah. Okay. Any questions?
Yeah,
Yes.
The non-existence of stable matching. Suppose you introduce randomization. Would that assign people at
random?
You give them some probability. I'm just trying to get the idea of
just
specifying by introducing randomization.
Assign randomly completely. Assigning people, matching people at random. That's what you're saying?
Well, there's some probability. I mean, there's an equilibrium set of probability. I don't mean any distribution. I mean, not an arbitrary. Supposing you tell people that you assign them certain probabilities.
With that have to do with their.
You have to have cognitive utilities. They have to bring in utilities.
That's a good question. I know. So there's those research results.
You don't see equilibrium.
Yes.
That's, I think has already been discussed yesterday. One way out of this is the exercise.
Yeah, so
I'm not sure.
I don't know. Well, that's a good question. I'm not sure.
You have to assume that you're okay. You have to obey. You have to obey what happens. That's true.
Okay. Yes?
I'm just not very clear about what causes the cycles. Is that because the hospitals or couples have cyclic preferences?
What causes the cycles is that what causes the cycles is the pair of positions, cycles in the couples graph or cycles of movements?
Cycles of the movement.
Yes, so a couple leaves, is rejected by some single, another job is suddenly empty. So someone can...
The hospitals have like a cyclic preferences, different hospitals have cyclic.
Oh, they don't have cyclic preferences, but if some couple is rejected, it causes some, by some single, that single caused some externality for some other hospital that makes some other position free and other things are moving around. But it's not cyclic.
The applicants also have
No, there's no cyclic preferences here. Yeah.
what causes the cycles are not related to preference.
It's the complementarities but the couples introduce into the market. That's what causes the cycles. Yeah. Let's start. So we'll take, yes. Let's.
What is the average rank of the couples who make the
Oh, so I don't know about average ranks here. I can guess, but yeah, but it also depends on short side, long side. We don't know much about this. Also, what happens when there's a small imbalance? This is both. Yeah. Okay. Thanks.